For decades, we thought we had this universe thing figured out. We had a really solid timeline of how the cosmos evolved. But then, the James Webb Space Telescope turned on its instruments, and we are now literally finding things that, according to our current models, simply shouldn't exist. Our classical understanding of the universe's history is being completely upended.
So we're starting our cosmic detective story with a massive, paradigm-shifting mystery. How exactly do you build a cosmic monster? If you look at standard cosmology, the early universe was supposed to be a kindergarten, right? A quiet place for galaxies started out as these tiny, isolated clouds of gas and dust, and they just slowly grew over billions of years. But instead of cosmic toddlers, we're finding fully formed galactic behemoths in this ancient epoch. It's literally like walking into a preschool and finding a fully grown adult squeezing into one of those tiny little desks. It makes no sense.
And trust me, the scientific community is genuinely stunned by this. Astronomer Dr. Joel Leja really hit the nail on the head here. He points out that finding these incredibly massive structures so early after the Big Bang is in severe tension with about 99% of our standard models for cosmology. They're so impossibly huge for their age that astronomers have actually started informally calling them universe breakers. Because look, either our measurements are completely wrong, which by the way we haven't found to be the case yet, or our fundamental understanding of the universe needs a total rewrite. Okay, let's dive into part 1, the universe breakers. There is this absolutely stark contrast between our old assumptions and this new reality. Standard cosmology told us to expect slow, localized growth. We thought dark matter halos captured gas and converted it to stars with a pretty low efficiency, around 20% or less. But JWST just spotted 3 ultra-massive galaxies within the first billion years of the universe that researchers are dubbing red monsters. And these things are converting their gas reservoirs into stars at nearly double the expected efficiency. They're highly accelerated star builders, somehow packing in stellar masses comparable to our modern Milky Way, but in a fraction of the time. And if you want to picture the sheer chaos of the early cosmos, look at this system known as JWST's quintet. This is sitting just 800 million years after the Big Bang. We aren't just seeing single massive galaxies here. We're looking at a highly compact, ongoing merger of 5 distinct galaxies, all at once. They've got a collective star formation rate of 250 solar masses per year, which is just astronomically higher than typical galaxies back then. But what's really wild is that they're surrounded by this extended halo of glowing oxygen-rich gas. Now, oxygen is only forged in the cores of stars, right? So this proves that these violent gravitational collisions were already ripping heavy elements out of early galaxies and scattering them into the surrounding cosmic web. Moving on to part 2, seeds of supermassive monsters. Because this universe-breaking growth isn't just about stars. When you look at how this builds a totally new picture, it's honestly jarring. Take a look at a system called Abell 2744 QS01. This was observed just 700 million years after the Big Bang. In our local modern universe, the ratio of a central supermassive black hole's mass to its host galaxy's stellar mass is usually about 1 to 1,000. The galaxy absolutely dwarfs the black hole. But in this early universe system, we're seeing a central black hole that is exactly equal in mass to its host galaxy, a 1-to-1 ratio. This completely shatters the idea that black holes always started as small stellar remnants and just slowly gobbled up material over billions of years. So to explain this massive timing paradox, like how does a black hole get so huge so fast, physicists are turning to a pretty radical theory, the direct collapse black hole. The idea is that under very specific conditions in the primordial universe, these massive, dense clouds of gas might not have fragmented to form stars at all. Instead, the entire gas cloud just collapsed wholesale, directly into a black hole, completely bypassing the stellar phase. The crucial takeaway here is that these primordial seeds did not start small like normal dead stars. If this direct collapse theory holds up, these black holes were born already weighing anywhere from 10,000 to 100,000 times the mass of our sun. They were born as absolute monsters, which gave them a massive head start in the cosmic race to become the billion solar mass titans we see later on. Which brings us to part 3, coevolution and cosmic engines. Let's see how these colossal black holes and their host galaxies actually shape each other across cosmic time. To really wrap our heads around this, astronomers looked at an ancient galaxy called MRG GM0138, back from when the universe was barely 3 billion years old. They used a technique called stellar dynamics, basically tracking the velocity of stars swirling near the center, to weigh the dormant black hole inside it. And the result? It tips the scales at a staggering 6 billion solar masses. But here's the catch. Despite housing this massive black hole, the galaxy itself is completely quenched. It's dead. It is no longer forming new stars. So why does that happen? Well, it comes down to this violent feedback loop that perfectly explains why galaxies like MRG 0138 stopped growing so early. First, you have the black hole going through a rapid feeding phase, where it ignites into a luminous quasar, releasing just unfathomable amounts of energy. Second, all of that violent energy heats up and literally blows away the interstellar gas supply within the galaxy. And finally, without that raw gas, star formation just instantly shuts down. The galaxy is quenched. Basically, the black hole burns down its own house, leaving behind a dead, inactive galaxy while it slips into dormancy. But the story definitely doesn't end when a galaxy goes dormant. Let's move to part 4, Echoes of Giant Collisions. Because eventually, these massive galactic islands drift toward each other in the cosmic ocean and merge. And when they do, their central supermassive black holes sink to the newly formed center and start this catastrophic cosmic dance. Now, we obviously can't always see these merging black holes with light, but we can actually hear their gravitational ripples. And that brings us to this groundbreaking discovery by the nanograph collaboration. They used arrays of millisecond pulsars, which are these ultra-dense spinning dead stars that act like incredibly precise cosmic clocks. As these binary supermassive black holes orbit each other, they rhythmically stretch and compress the fabric of space-time itself. By monitoring the exact arrival times of those pulsar signals over 15 years, astronomers detected the low-frequency gravitational wave background. It's a literal cosmic hum generated by merging supermassive black holes all throughout the universe. Finally, let's zoom all the way out for part 5, the grand cosmic web. We've talked about early stars, universe-breaking black holes, and the gravitational hum of their collisions. So how does all of this fit into the macroscopic structure of our reality? This spatial timeline really grounds us in the unimaginable scale of the cosmos. Think about this for a second. Our entire human influence, the absolute furthest reach of all our radio broadcasts, is just a tiny bubble 100 light years across. Now compare that to the Milky Way at 100,000 light years. Zoom out further, you get the local group, then the Virgo supercluster, and finally we reach Laniakea. It's a Hawaiian word that means immense heaven. Laniakea spans 500 million light years and contains the mass of 100 million billion suns. This is our grand galactic home. Yet even something as massive as Laniakea is just a single node bound together in something vastly larger, the cosmic web. It is the largest pattern found in nature. A monumental lattice where galaxies and superclusters are strung together along glowing filaments of dark matter and gas. And in between these glowing highways, you have the voids. These are vast, terrifyingly empty regions of space, like the Beauty's Void, which spans 330 million light-years across but contains almost absolutely nothing. So, what does this all mean? We live in a universe that is far more dynamic, aggressive, and fast-paced than we ever imagined. With our standard models being broken by red monsters, impossible black holes, and the hum of gravitational waves echoing through the cosmic web, we are standing at the edge of a totally new frontier. Humanity is peering deeper into the cosmic dark than ever before. So, I want to leave you with this. What other impossible cosmic monsters are out there, lurking in the web, just waiting for us to turn on the lights? Keep looking up, because the universe is just getting started.